Hi everybody, it's Mr. Ducrane, and I'm going to teach you a little bit today in this video about square root and other inverse power functions. When I'm talking about square roots, I'm not talking about roots that grow in squares. I'm talking about the mathematical operation that lets us solve things like the Pythagorean theorem, or to model the movement of a pendulum or a kid on a swing, or even to run collision detection algorithms in a video game. Square roots can also help us make pretty pictures on a computer, which also help us to run computer-generated landscapes. But let's get down to some basic things. First, take out the handout that has the grids on it, and what I'd like you to do is pause the video and make a nice table of values and a good graph for y equals x squared. Do this with a partner to make sure you're doing it right. I'll wait here, pause the video and do this, please. Good, I'm glad you did that. Hopefully your graph and your table looks something like this. We'll come back to that in a minute, but go down to the next table and do the same thing here. Again, you pause the video and do this, and I'll wait for you here. Again, hopefully your graph looks something like this and your table too. This shouldn't be a surprise. We've been looking at these kinds of functions for a couple of days now, and remember, when you have an odd exponent, you end up with n behavior as x goes to infinity, y goes to infinity, as x goes to negative infinity, y goes to negative infinity here. That's something you've seen before. Okay, one more time. What I want you to do is go back to both of these, and I want you to do the inverse. Remember how to do an inverse? Swap the ordered pairs. So we're going to make another table of values here for the inverse, and then you're going to graph those ordered pairs and plot the new graph. Do this for both the y equals x squared and y equals x cubed. Again, work with a partner to make sure you're doing it right and you agree with each other, and I'll wait for you here. Pause the video. Okay, so here's our inverse of y equals x squared. We just swapped the ordered pairs around and we plotted the points, and you've got that sideways parabola. And again, remember, when you do an inverse graph, you should see that symmetry across the line y equals x, and that's how you know that you've got an inverse. That's the inverse for y equals x squared. And here's the inverse for y equals x cubed. Again, you can see that symmetry across the line y equals x. If you fold it along that line, you can kind of see that the two halves match up a little bit. Something interesting to notice here, the inverse of y equals x cubed is actually a function, because for each input there's only one output. But if we go back to the inverse for the y equals x squared function, here we have a problem, because for some inputs, like for 4, we have two different outputs, -2 and +2. Since we have two different outputs for the same input, this is not a function. What we'd like to do is make it a function. So what mathematicians do when they run into this kind of situation is they only look at the part they're interested in. So we're only going to look at this top part. If we only look at the top part of the graph, we get a function. That's these points. And you'll notice, by only looking at the positive values for y, we eliminate those duplicated x values in there. And so each input, if we only limit our domain here, each input only has one output. And so we're only going to look at the top half of that graph. By the way, remember how to do an inverse. If we swap the x and y around in the equation, we get x equals y squared. And you might ask yourself, how do I solve for y? What undoes squaring? And here's where the square root function comes in. Square root of x equals y. And so that's our inverse function. I'm going to write it as y equals square root of x. And that's the inverse function. Sometimes we can also write that as y equals x to the 1/2 power. It means exactly the same thing, it's just a different way of writing it. Both of those give us this highlighted graph over here. The inverse of y equals x cubed, we don't have to limit the domain here, because the inverse is already a function, so we can look at that entire thing. This whole graph is part of the inverse. And again, if we kind of switch the x and y in the formula, we get x equals y cubed. And if we want to undo the cubing, undo to the 3rd power, we take the cube root. So we write it this way: the cube root of x equals y. By the way, this little number here on the radical sign, that's called the index. And if we don't write an index, we assume it's a square root. Otherwise, if we want a cube root or a 4th root, we write the number there. We can also write that as y equals x to the 1/3 1/3 power. Y equals x to the 1/3 is the same as saying y equals the cube root of x, and all that means is we're looking at that entire graph. So let's talk about these root functions, or these inverse power functions, as a group. So we've got y equals x squared, and the inverse of that we already saw is y equals the square root of x, or y equals x to the 1/2, and it looks something like that. Again, we only want that top half so that we're looking at a function. By the way, if we talk about the domain and range, the domain on this, notice we start here at 0 and we just keep getting bigger. So it's 0 is less than or equal to x is less than infinity, or just x is bigger than or equal to 0. The range is the same thing, since that's also the bottom of the graph. It's 0 and above, so the range is from 0 to infinity as well. The cubed function has the inverse y equals the cube root of x, or y equals x to the 1/3, and we saw we want both halves of that graph like this, and we still have that center point. Remember, that's an inflection point right there at the origin. The domain here is everything. This graph doesn't stop going left or right, so it's everything between infinity and negative infinity. And the range, even though it looks like it's not growing very much, this is getting bigger, but very slowly. If we were to expand this window out more, we would see this graph would keep going up, so, and down for that matter. So the range on this graph is also from negative infinity to infinity. Okay, that handout you were doing the graphs on before, turn it over, and what I want you to do is decide what you think the inverse of y equals x to the 4th looks like, both as in terms of a graph and in terms of the formula. So sketch out this graph on the back, make a prediction, pause the video while you do this, and I'll wait here for you when you're done, and then you can check. So pause the video and check it. You got your prediction? Okay, here's what y equals x to the 4th looks like. Again, if we're going to do the inverse, we've got to reflect this graph across the line y equals x. And so if we do that whole graph, it's going to look like this. But again, that's not a function, so mathematicians take it upon themselves to say, well, if we want to make it a function, we're just going to ignore that bottom half. So this is what the 4th root function looks like. If I write it as a formula, it's y equals the 4th root of x, or y equals x to the 1/4. And again, the domain is from 0 to infinity, and so is the range. Okay, again, pause the video and do the same thing for y equals x to the 5th. Find that inverse power function for y equals x to the 5th. I'll wait here. Okay, so here's the inverse power function for y equals x to the 5th. It's either y equals the 5th root of x. We say the 5th root of x, or if we write it as an exponent, it's x to the 1/5 power. And here's the domain and range as well, so please make a note of that and how we read that. You may be wondering, what's the real difference between this 5th root function and the cube root function? They look a lot alike, DeCrane. Why are you showing us two different functions? Well, just like the cubed function and the function for x to the 5th, x to the 5th is a little bit steeper on the sides and more flat here in the middle. Same thing here. This is flatter on the sides, even though it does continue to get bigger and smaller in the y direction, but it's also a little bit more vertical in the middle here than y equals x cubed. So there are some changes, but they have the same basic idea. Okay, let's do some transformations on these new functions. They're going to move around just like the old functions did. So here's our graph of y equals the square root of x. If I want to graph y equals the square root of x plus 4 minus 1, this is going to do the same kind of transformations as before. This plus 4 that's inside the function means we're going to shift left 4 units, and the minus 1 means we're going to shift down 1. And so I basically take that middle point, this one right here at the origin, and that's what's going to move to the left 4 and down 1. And then we can just kind of sketch the graph, and it's going to look something like that. And notice now the domain and range change. The domain on this one is from -4 to infinity, and the range is from -1 to infinity, because I moved that endpoint around a little bit. In general, this works just like all the other transformations we've been doing. We can write it two ways. We can do y equals a times the square root of x minus h plus k. And again, h and k is where that center point, or in this case that end point, moves around. And a is kind of, we've been talking about as the slope or the steepness, still does the same kind of thing. If we write it using exponent form, it would be y equals a times x minus h. And here we're going to do 1 over n plus k. And by the way, that n is really the index there. If I don't write the n, that means the square root. Here I have to write the n as 1/2 if I want to do that. But that's the two forms for the same kind of functions. It's the root function, which can be written as an exponent with that 1 over a number in the exponent. So what I'd like you to do is, again, pause the video, and I want you to try one. Here's our cube root function, and what I'd like you to do is make a graph of y equals the cube root of the quantity x minus 5 minus 3. Pause the video, predict what that's going to be, make a sketch on your own on the back side of your handout, and talk about the domain and range with your partner as well. And then when you're done with that, restart the video and I'll show you what I got. So again, keep in mind what's happening is this minus 5 means we've got to shift right 5, and the minus 3 outside the function means we shift down 3 units. And so I'm going to take that center point, this guy right here, and that's what I'm going to move over to the point here, 5 comma -3. It shifts to the right 5 and down 3. And then I'm just going to pretty much rough in the function again, and it looks something like that. And again, since it keeps going, the arrows go in both directions, left and right. They're also heading up and down, although not very steeply at all. The domain is still from -infinity to infinity, and the range is also -infinity to infinity. Okay, let's do one more, and let's talk about modifying a little bit. What if we were to do y equals the negative of x plus 2 to the 1/2 plus 8. And that negative sign, remember what that negative did in all of our other graphs? That kind of reflects it vertically. The plus 2 inside the function means we're going to shift left 2. And the plus 8 outside the function means we shift up 8. And you may be thinking, what is it that we're shifting? Well, we've got to remember what's the parent function on this. And since we've got that 1/2 here in the exponent, remember we can also write this as y equals -1/2. Remember, means the square root. I don't have to write the 2 there. I could put a 2 there, but I don't have to. Y equals the negative square root of x plus 2 plus 8. And here I'm just going to do a really rough sketch, a 10-second sketch. So I'm going to draw my axes. I know my end point is at -2 comma 8. So I'm just going to say it's right about there. And typically a square root function would look like this, right? Heading upward. But that negative in front of the square root sign means that it's actually going to be reflected downward, and it's going to look something like that. And so the domain here is from -2 to infinity, and the range now, because that endpoint is now the top of the graph, is going to go from -infinity, because I'm heading from down here up to that top, so that's less than y is less than or equal to 8. So that's the point, -2 comma 8 is that endpoint. And so that's the graph of y equals